are becoming, how do you pick what to put on the chip? So that's choosing the physical RAM blocks that you actually put on there and the RAM mapper can use. Okay, let's see. We've got okay, I don't have an update on the score though. So I am counting on the Zoom people. I know the people on Zoom that you have another window on your desktop with the World Cup open. I'm not offended. It's totally fine. You can post the score if you want. So let's see if I can make this advance. Okay. Okay, so we're looking at, okay, so I should actually check. Probably everybody else is curious now. So oh, it's over. It's already over? I thought soccer, okay, so I gotta admit, I'm not the world's biggest soccer fan. I thought soccer games took a really long time. So, okay, anyway, I guess that is still, against a tough team, that's still not a bad performance. Okay, so let's talk about physical RAM. So I guess the most basic building block we have is the SRAM cell. And an SRAM cell looks like this. So back-to-back inverters. So that forms, let's see if I can make this draw. So this forms a latch. And then we have two access transistors, here and here. And I talked about this a bit earlier. SRAM design is actually kind of tricky. You have to design the pull-ups on these inverters to be weak enough that you can, whichever side has a 0. So if I want to write a 0 into this cell, whoops. If I want to write a 0 into this cell, I put a 0 here and a 1 here. And the idea is that this 0 pulls this node low enough that eventually, basically is able to overpower this inverter. This node goes low. If that node goes low, this node goes high, and now this inverter stops fighting. Okay, so there's a bit of tricky design to making sure that these access transistors are strong enough that during a write, when you basically put a 0 on one side and a 1 on the other, that they can overpower the latch. But during a read, when you also turn on these transistors, you don't upset the cell. You don't flip its state. Okay? But this uses 6 transistors per cell. And maybe, does everybody know how this works? Maybe I should say it. Like a word line goes high. So if I want to read or write to a certain row of the RAM, I basically have a decoder. The address is presented to the decoder, and it figures out, which row of the RAM are you trying to write to. So every address maps to a different row. Maybe I'm trying to write to this row. So that word line goes high. That word line goes high, turns on this transistor and this transistor. And there are read-write circuits up here. Okay, so there's a write driver. So the write driver is a big buffer up here that basically will strongly drive this. Let's say I want to write a 0. This goes to 0. This will strongly drive this to 1. And the cell will flip, right? Doesn't matter if it was storing a 1 and a 0 before. Basically, this is strong enough that this is going to turn into a 0, that'll turn into 1. So we write the cell. To do a read, we actually use the exact same circuitry. Okay. The word line, we decode the address. The word line goes high. This transistor turns on. This transistor turns on. But this time, we don't turn on these powerful write drivers. Okay, these big buffers that can strongly drive those bit lines, we don't turn them on. Instead, what we do is before the word line goes high, we actually pre-charge this line to VDD over 2 and this line to VDD over 2. Okay? So, and what that does is, with that smaller voltage difference, let's say I have a 0 here and a 1 here again, I won't flip the cell. Okay? So you have to carefully design these transistor ratios that when you have not a 0 on one side, but just a VDD over 2 on both sides, you don't upset the cell. Now what happens is so this latch stays in its current state, and this side is going to be trying to pull this bit line down, because this inverter is driving out a logic 0, right? It's sinking current. And this side is going to be trying to pull this bit line up. So what happens is they pull the bit lines apart. And to make your SRAM fast, basically these cells are pretty small, right? These are usually all minimum or very close to minimum size transistors. And we've got a bunch of them hanging off of a bit line. So here are my bit lines going down here. So I might have, 64 or 128 or 256 rows. So I've got that many SRAM cells hanging off of those bit lines. So that means these bit lines are fairly long, and they got a lot of transistors hanging off of them. So they're quite capacitive. So to make the SRAM read relatively fast, we don't wait for one of these bit lines to get pulled all the way to 0 and the other one to get pulled all the way to 1 during a read. We just let them get pulled a little bit, maybe 30 millivolts. So this might be pulled down after some amount of time to 30 millivolts lower, and this one might be pulled 30 millivolts. Actually, it doesn't get pulled up very much, so it might get pulled up a little bit. The pull-ups are weaker, so maybe it gets pulled up 10 millivolts. So a voltage difference develops, and then the RAM basically activates sense amps. So that's what these circuits are. So there's one sense amp tied that's basically got, it's a differential amplifier. That's what a sense amp is. So there's a sense amp up here, and it's got these 2 bit lines going in as its inputs. So one positive, one negative, and it just detects which one is higher. Okay, and if it detects that this side is higher, then it read a 1. If it detects that this side is higher, then it read a 0. Does that make sense? So inside a RAM, there's actually all sorts of tricky, what are called self-timed circuits. Self-timed circuits just means they're like delays. A clock hits the RAM, and this pre-charge starts. So a circuit kicks in and starts, and it detects that it's supposed to do a read. It starts pre-charging both these to VDD over 2. Another delay happens, and then this word line, this decoder has finished decoding, and the word line is activated. So again, there's like a self-timed or delayed circuit, basically, that drives this to a logic 1, and then it waits a little while longer, and then it turns on the sense amp to actually determine which way where the voltage is pulled apart. Okay? Then the next cycle, you repeat the whole thing. Okay? So it's all keyed off the clocks, but they're all these self-timed circuits inside. And if the next cycle was a write, then it'll do things a little differently, right? It'll do that, turn on the right drivers to pull this, say strongly to a 0 and strongly to a 1. But otherwise, the rest of the timing is pretty similar. Does that make sense? Okay, so that's base. How many people knew that, actually? It's always useful to know, like, am I just telling you things you already know or not? So how many people knew how an SRAM worked? Okay, anybody, like, so some people did. How many people didn't know how an SRAM worked? Okay, so we're going to keep talking about that then. So it's useful feedback for the future. Thanks. Yeah, SRAM design is actually pretty interesting. It's quite tricky and also very important. Yeah? SRAMs, modern SRAMs are all synchronous. Okay, what it means by synchronous is they are activated by a clock. So if you go back far enough in the past, back in the day when I was an undergrad, okay, so it's probably farther in the past than any of you were studying engineering, SRAMs were actually asynchronous. Okay, so you actually changed you just changed the address inputs here, and if you had the read enable signal high, data would come out. Nobody does that anymore. Okay, the reason they don't do it is it's too complicated, because I just described a whole bunch of signal timings inside the RAM. The clock edge hits, there's a delay, and then the clock edge hits, it detects it's a read, it'll start pre-charging right away. There's a delay, then it basically activates the word lines. There's another delay, it activates the sense amps. That's all a lot easier to do if you start with a clock edge. If you don't start with a clock edge, if you actually make what's called an asynchronous SRAM, you have to actually detect when the addresses change and then basically start all those timers. That's kind of a real pain to go make a bunch of circuitry just to figure this out. So yeah, maybe 20 years ago, 25 years ago, people just went, we're not doing this anymore, right? You give us a clock. Does that answer your question? So all of these SRAM blocks that I'm showing you are synchronous. Okay, I guess I just told you all that stuff. Okay, so I just told you all of those things. Okay, so what I just showed you is a single port RAM. Okay, so there's an array of cells. Okay, so some number of rows, and some number of columns. The number of rows defines how many bits go into this row decoder. The number of, and how many things are hanging off of each bit line. The number of columns decide how many sense amps do I need, because I need a sense amp for every single bit line, bit line pair. And yeah, what I've shown you is a single port RAM, meaning it takes one address in, and I can either do a write or I can do a read, but I can't do both. There'll be some control signal that I haven't shown here that's read or read slash. There'll be something like read slash write bar, and that would tell me which one I'm going to do. Okay, now most FPGAs, you can build this on an FPGA, so we can make our physical RAMs out of this, but it's kind of limiting. Because a lot of FPGA RAM is used for FIFOs. And a FIFO, fundamentally, you want to be writing into it in one spot, and you want to be reading out of it in another spot. And usually, like most clock cycles, you're going to do both. So that really makes you want two ports. You'd really like to have a read port and a write port and be able to use them simultaneously. So to build that, to build a dual port SRAM it's a tweak on what I just showed you. Okay, so we still got our latch. Okay, so heart of an SRAM is actually a latch. So I got these cross-coupled inverters. And what I've shown in blue here is what you had before. Right? We have an access transistor to our bit line, and the complement to the bit line. And we have a word line that turns those access transistors on. So blue, everything that's in blue is stuff that I just showed you. What's new is what's in red. And what's in red is just another copy of the access transistors and the bit lines. So I have another access transistor on each side. I have another word line, so word line B. And I have another bit line bar, well, bit line B, and I have its complement. Okay, so to build another port into an SRAM, I basically build another set of access transistors, right? So access transistors that can connect me to a different set of bit lines, and those access transistors are controlled by a different word line. Does that make sense? What does this do? Well, I need 8 transistors per cell now. So my transistor count is not free. To get the second port, I had to increase my transistors per cell by 33%. So it's not catastrophic, but it does cost me something. Then when I go to turn this into an actual SRAM block, I make a cell array just like I did before, but I'm now using these slightly bigger cells, 8 transistor cells. And to make 2 ports work, I have to send in 2 addresses. So I have my old address, and now I have my new red address. Each of them needs their own decoder. Okay, so because I'm going to decide which row address A is talking about, so I need a decoder to decide that, and its outputs are hooked up to basically these word line A's. And then address B I also decode, and its outputs are hooked up to the other word lines, word line B. And then to do the actual read or write, I basically need 2 different sets of read-write circuitry. Okay, so I need to have my port A read-write circuitry, and I need to have port B read-write circuitry. Okay, so does that make sense? Yeah. In here? Yeah, this is now you get into stability. So yeah, you have to be careful that these inverters are strong enough that when you do a read, if both ports chose to read from the same cell, that it wouldn't upset it. So you're right, your stability also gets a little more tricky. And maybe that means you have to change the design of these inverters. So there might be some additional area increase for that too. It's the area. So the inverters don't really change that much. You do have to check their stability, but usually you can still keep them small. It's basically for every port you add, you're adding these access transistors, and you're creating another decoder, and you're creating another set of read-write circuitry, okay? So your area keeps going up with every single port. So there's not much of a limit. You can make actually highly multi-ported memories. So if you look at processor register files, they actually have a lot of ports. Because a processor, it's the centralized memory issue in processors. You build a register file, you hook all your functional units to it, and you got a whole bunch of functional units. Turns out you now need a whole bunch of ports. So the SRAMs that form register files in processors are highly multi-ported, and that makes them bigger. It also starts to slow them down some, right? So there's some cost to that. For an FPGA, the main cost of making your physical RAMs have more ports is area. They just get bigger and bigger. Now, if you needed highly ported memories all the time, then you should just do it. Because we also saw that, when you have if a person asks for lots of ports and you only have, we did it with 2 ports last week, it's pretty painful, right? Like, it's pretty painful to make the user more ports when your physical RAM doesn't have many. So if you need a lot of ports, then probably you should build highly multi-ported RAMs. But if you don't usually need that many, it's definitely not free. Does that make sense? Yeah. You're saying like, you're saying what if you're trying to write the same row at the same time? So that is basically documented in like the vendor data sheets of don't do this. Like if you try to write 2 different values, so basically the question is, well, what if you do things like you send in address, I don't know, 12 here, and you also send in address 12 here, so they both activate their word lines for the same row, and they've both been told to do a write, and the data is different. What happens? You don't know, right? Like nothing good, okay? Some unknown data will be written. The vendor data sheets basically say don't do this, right? Because while the RAMs physically can do it, it doesn't make any logical sense. So in your design, you should make sure that never happens. Reading while you're writing to the same cell is allowed. Okay, so reading 2 different rows, is totally fine. Both ports reading from the same row, also fine. One port writing to the row and the other port reading from that same row is electrically legal, but it's ambiguous. Do I get the old data before the write, or do I get the new data before the write? So if you look very closely in the IP, when you write Verilog, it has a certain behavior. Okay, so if you just write Verilog, you will get one of those behaviors. I think it's the new data, okay, because that's just the semantics of if you wrote an array in Verilog, that's what it would mean. If you instantiate a memory block by you can go into the IP cores in the vendor tools, like Quartus or Vivado, and you can say, I want a memory block, like this logical memory. If you instantiate a logical memory, one of the advanced parameters you can set is what happens in that case. And the way that that's done is the RAM itself has some natural behavior. I think the natural behavior is we don't know. Okay, so if you want the fastest timing, you actually say, I don't care. Like, I'll never do that. I don't care what happens. If you say, I want the old data, then the timing of the signals will be changed. Quartus or Vivado will program different signal timings into the RAM block, because it's got a little bit of configurability there too. And what happens is it'll actually delay the read. The read will be done after the write is completed, and you'll actually find that your timing is worse. If you said, I want to get so that's if you want to get the new data. If you say, I want to get the old data, the write will be delayed. So the RAM has the ability to delay the timings under control from the CAD system. By default, it just doesn't guarantee anything in that case, and you get the best timing. Does that make sense? Any other questions on that? Yeah. Yeah, that's a good question. So most FPGA RAMs are built out of what's called a true dual port core. Okay, so that's what I've shown you here, where both ports can do read or write. And that's the most common way you design an FPGA RAM. It does make the electrical design of the RAM cell a little more tricky, to sort of guarantee it's stable even if you do 2 reads and stuff like that. I know Stratix 10, so a recent Intel FPGA, actually changed its RAM core so that it actually basically made a dedicated read port and a dedicated write port to make it easier to design it. So usually it's what I've shown you here, which is like a true, like a read-write core, where you have 2 ports that can do either. But there's at least one FPGA that didn't do that in order to make the RAM design easier. Does that make sense? Okay, so yeah, but there's a cost to this. My SRAM cells get bigger, and I basically need 2 copies of my decoders and my sense amps and so on, so I get double the peripheral circuitry. Okay, so let's talk about what this costs. So larger RAMs are more efficient per bit. So if I look at this and I say I just want the most bits, then what I want to do is make this cell array really big. Okay, because by making the cell array really big, it essentially amortizes the costs of these read-write circuits, the decoders, etc. more. So the RAM is getting bigger, but my cost per bit is dropping, and it drops to some asymptote. Eventually the cost per bit, is this. Like, it can never get better than that. Okay, so if that's what I thought my end users needed, they just needed lots and lots of storage, then I should build big physical RAMs. And this is a model of area with some arbitrary constants that is reasonable. And this is what you actually have in assignment 3. So there's some cost to just make a block RAM for all those self-timed circuits and so on. I told you need delayed versions of the clock. You need to figure out, am I doing a read or write on a certain port, etc. So there's some cost to just putting all that circuitry in. Then there's another cost, which is, oh, actually, sorry, this cost is, I misread it. Okay, this is the most basic cost, some cost per bit, okay, just the SRAM cells. Then there's another cost that is proportional basically to the square root of the bits, which is all that peripheral circuitry. So I haven't really proven this, but you can kind of get an idea that, hey, the cell array is square and the peripheral circuitry is all around the edges. So it seems like that would be about square root size, and it actually is. Okay, so those are the write decoders, the read decoders, the row decoders, and the sense amps and stuff. That's this some other constant times the square root of the bits. This C3 is just the cost of making those delay circuits and a little bit of circuitry to decide, are you doing a read or write, etc. And then there's something that's specific to FPGAs, which is some cost times the number of routing ports. So I have to hook up to the programmable routing, and every signal I hook up to the programmable routing I actually know involves some multiplexers, etc. And we saw those are pretty expensive. So that's going to be part of our block RAM cost as well. Does that make sense? So if I just want to get the most bits in a certain area, I should actually make my physical RAMs really big. But if I do that, there's a high chance that I waste some of the bits in a lot of applications. So maybe you built me a 512 kilobit RAM. That's what the physical RAMs are. But I have a whole bunch of little scratchpad memories that are only 4 kilobits. So I'm just going to, in my design, I'm going to waste most of those huge RAMs that you built me. So as you make bigger physical RAMs, there's a higher probability that some of the bits are wasted by many of your end users. You also, it's not just about how many bits are in the RAM. I need a certain number of bits to store all my words, but I might want wide words, maybe 128 bits wide, because my data path is 128 bits wide, and I need to feed it a new 128-bit word every cycle. If you make a RAM that can't accommodate that, it has enough storage to store all my 128-bit words, but it doesn't have enough inputs and outputs. I can't actually use words that wide. Then I can't fully exploit that. I have to use multiple physical RAMs to kind of gang them together in parallel and get my physical word. And that's another way that I might wind up wasting some of a big physical RAM. It just doesn't have enough routing ports, enough width. So even though it might have enough bits, I need to use a bunch of them together in parallel to get the bandwidth I need. So this is like a classic trade-off. You can't look at this and just say, okay, obviously you should make big RAMs, or obviously you should make small RAMs. There's a trade-off for each one. One of the things that almost all FPGA RAMs do to help with this is they add a little bit of extra circuitry to the RAM that you wouldn't find in an ASIC or a processor to make the physical RAM configurable width. Okay, so what does that mean? So it might mean that the physical RAM we built might be 1,024 words and times 8 bits wide. Okay, so that's like the natural organization of the RAM. But we can add in a few multiplexers that are configured by the CAD tool based on what you're trying to do that say, well, you could just take that data and just send it out to the routing channels. Or we could like multiplex. We could look at one address bit and basically multiplex between pairs of 4-bit outputs and just send that to the routing. Or we could look at 2 address bits and multiplex between sets of 2 outputs. Or we could look at 3 address bits, and we could actually multiplex all of those, that 8-bit word, to choose which bit within it did you actually want and send that out to the routing fabric. And the cost of that's pretty small. Okay, this is a few multiplexers, and we can build those multiplexers right into the RAM, so we're not having to build them out of logic cells. We can build them into the RAM. They'll be pretty efficient. Does this make sense? So almost all FPGA RAMs do this, where they have this configurable width circuitry to make them a little more flexible. Yeah?
Does that mean each more is
Yeah. What I'm saying here is that the actual RAM array, if I went back here, I'm showing here read circuits. There's actually some muxing here too, which is called column muxing. So usually I don't actually build one sense amp for every single pair of bit lines. I might have muxing that allows me to choose between 4. So let's say I built this so that it naturally produces an 8-bit output, okay? And that means I need 8 sense amps, and it has 1,024 words. So that's what I really built. FPGA block RAMs add a little bit of extra circuitry after this normal RAM circuitry to allow you to do a little more multiplexing. Does that make sense? And the CAD tool just chooses whether you want that extra multiplexing or not. Okay, so this is like a complicated picture. Don't worry, you have to memorize it all. This is basically the RAM core that I just showed you, which is basically the same RAM core you'd put in an ASIC or a processor. And then around it is, well, what are the additional things that go into an FPGA? Okay, so one thing is we need to have routing ports. Okay, so we've got all these routing, we've got some local interconnect here and multiplexers to choose from that local interconnect what goes into every one of our data inputs and every one of our address inputs and so on. Okay, so that's just, and to get to this local routing, we had muxes from the general routing. Okay, so this is just all the island-style FPGA circuitry we've seen before. It's very similar to what you would have to go into a logic block. But it's costly, so it's important to remember that it's there. We also have routing ports for our outputs. So the outputs from this RAM block, we can, in most FPGA RAMs, you can choose whether to register them or not. So you have this little optional register circuit. And then basically they are inputs into our switch block multiplexers, like the multiplexers that drive the routing wires. And that's how we get our outputs out. And this is also costly. So there's a cost for every input. There's a cost for every output. And then, like I said, I didn't circle this. These things are one particular implementation. And if you're interested, you can go look at this paper to see the details. This is one particular implementation of that width configurable multiplexing, where a few SRAM cells in here are programmed by the CAD tool, and they basically decide, do I want all 8 bits that are the natural data word of this RAM coming out? And do I want all 8 bits going in when I do a write? Or do I actually only want to provide 1 bit and have essentially more words? And this multiplexing and control circuit will make that happen. And it's not that big, okay? Because it's not that big compared to the RAM array, which is big, or these routing ports, that's why pretty much all FPGAs include it. It makes it more flexible and it's pretty cheap. Does it make sense? This is like what's leading to the area model that you have in Lab 3. And the area model I gave you in Lab 3 is realistic. I mean, I basically curve fit it to data from like real FPGAs that I was part of the design team of when I was at Altera. Okay, so that's kind of how we build RAMs. Now let's talk about how an end user, like a designer using your FPGA, uses the RAMs. So, so the simplest RAM would be a single read-write port. So I'm talking here about like what the person is instantiating in his or her design, asking for. Any ideas of like what might I put in a single port RAM? What would be a reasonable thing? So single port RAM means I can do a read or I can do a write, but I can't do both on one cycle. Okay, that's a single port RAM. And that means I have one address input, and then I have one data input, that's like the data word that comes in for a write, and one data output. That's the data that comes out for a read. Now I can't use both of those input and output at the same time, but generally I'm going to have to build both an input and an output, even though I don't have to use them at the same time. But I only have to build one address input. Okay, so that's what I have to build. What would I use this for? If nobody ever uses it, then I don't have to worry about it. What do you think? What's that? A FIFO? It's not a great match for a FIFO because, I mean, technically you could build a FIFO out of it, but basically you can only read in a cycle or write in a cycle. So on a lot of FPGA FIFOs, you really want to be able to do both, rather than say you got to wait. If you think of how we were using FIFOs to kind of decouple modules and streaming computations, it's going to be really inconvenient if you say I can write into this or I can read from it, but I can't do both because we're actually using them to figure out when to stall and so on. So yeah, not usually FIFOs. Go ahead. Yeah, so actually ROM. Maybe there's a bunch of constants that I need. Okay, one port's fine for that. So that's a good idea. Another one is actually program memory. Okay, so say that I've got a soft processor or I'm using a processor style control. Maybe I've made a big hardware engine, but there's a processor that's sort of setting all the control signals using SIMD or something. I only need one port to read my instruction memory. And I could have loaded that instruction memory a long time ago. So I can write to all the instruction memory when I power up my system, and then I can just read from it all the time. I shouldn't have like self-modifying code and stuff. That's like madness. So yeah, so program memory, constants, and it's cheap. Okay, 6 transistors per bit if I only build that in my physical RAMs. And then we have to think about the routing ports, because routing ports, again, are always so expensive when you're connecting to programmable logic. So for inputs, we have the address bus, and we have the data bus to come out. And the data bus coming out is, I'm just going to call it width. It's like what's the maximum width word that I said I could get out of this RAM? So we'll call that width bits. And then I also need, sorry, those are all the inputs. So this is actually the data in. That's the data being sent in for a write. When I do a read, I'm going to send data out. So and it's going to be the same word width. So I need width bits of data output. So does that make sense? Okay, so that's the cheapest kind of memory I could build in an FPGA, but it doesn't capture all my uses. So one read port, one write port, which FPGA data sheets usually call simple dual port. Okay, so what's that used for? So I'll go back to you. So what do you think that was used for? Yeah, so this is the perfect case for FIFO. Okay, and I'm drawing up here what that one, actually this is just me drawing that you can't actually have a read-write bus. So you have to build a read data and a write data, like an input write data and output read data. Okay, so simple dual port, FIFOs are the killer app. A little more expensive, 8 transistors per bit so that we get the second port. And then we have to go count the routing ports. Okay, so we actually still just need one output for the read data and one input for the write data. So that's actually pretty good. We now need 2 separate address inputs, a read address and a write address. So we need a little bit more routing ports, but only whatever our address width is. Maybe we've got 11 address bits, but we need 11 more routing ports. So it's actually not too bad. So that's why this is a pretty good choice. Not many more routing ports, a lot more functionality. Okay, so we could also do, okay, true dual port. So true dual port says I got 2 ports again, but they can be either read or write. So I could do 2 reads on one cycle, 2 writes on another cycle, and 1 read and 1 write on a different cycle. So it can do everything that simple dual port can do and more. So Any ideas? You might have actually seen this quickly. Like, any idea what this is useful for? What do you think? Faster FIFO? You don't really, for a FIFO, you do fundamentally have one input and one output, so it doesn't really help you with FIFOs, because you're just going to basically be writing something into one part of the FIFO and reading something from another part, so you don't really need anything beyond simple dual port. I guess you could, but no, this would be kind of weird FIFOs that can only do one thing. So I don't know. In theory, yes, but in practice, people don't really do that much. It's basically moving towards some of the things we talked about processors. So if you think of processors where they have centralized storage, they usually have a lot of ports on their register files, and they have a fair number on their caches usually, especially first level cache. So yeah, something where I don't know my access patterns that well, which register files in processors and caches can often be, I might need to do 2 writes this cycle, and most of the time I want to do 2 reads. And so that can be helpful to have true dual port. But it's more expensive. So it doesn't cost more in the bits per SRAM cell. That's still just 8 transistors. But it does need more routing ports. Because I now need a data input for writing on one port and a data output for the read, and I need to replicate that for the other port. So yeah, so basically I need significantly more input and output ports versus simple dual port. Okay, and then we could do more. We could do 2 read ports and 2 write ports. So that would be called, sometimes it's called simple quad port. Okay, it's 4 ports, but with some restrictions. So we'll call it simple quad port. This is actually done. It's been done in at least a couple FPGAs. So it is useful for register files. I told you register files have can have a lot of ports. Also shared memory switches. So a shared memory switch means it's like an alternative to a crossbar. Like I write data in using some ports and I read data out on another port. And that actually forms a switching function. So it's used in packet switches sometimes. Write all the packets in from a whole bunch of different ingress ports, read them out on a whole bunch of egress ports, and just by reading and writing to different addresses, I can actually implement the switching function. But it is getting more expensive. Okay, so this needs 12 transistors per bit to get those 4 ports, and I need a whole bunch of routing ports to get all these address and data ports in and out. Has been done. So it was done in an Altera chip called Mercury. Turned out, so we experimentally verified that there is not enough demand for this. Okay, well, it's useful for things like shared memory switches, not enough to justify the cost. So it hasn't been done a whole lot since. Okay, so what most FPGAs do is they actually build this true dual port RAM. Okay, we need 2 ports for FIFOs, so we need either simple dual port or true dual port as kind of our minimum. And the cost of true dual port, if you look back here, was not much higher than simple dual port, except like the cost of the SRAM array was the same. What it needed was more. It needed more input and output routing ports. Okay, so the difference between it was basically an extra width worth of routing ports on both the input and the output side. And that's not a trivial cost because routing ports are so expensive. So the solution, basically the trade-off that most FPGAs make, is they'll use this true dual port RAM cell or RAM core, but they won't build enough routing ports to use it in its maximum word width. Okay, because those extra routing ports are just too expensive. They don't want to put them in just to allow true dual port with wide words. So they'll just build the number of routing ports that is needed for simple dual port. So you can use, let's say that the maximum width, like the normal width of the RAM was 32-bit words. So you have to build 32 data inputs, 32 data outputs, plus a couple of address ports, just to make simple dual port work. True dual port would need more, but you don't want to build that because it's too expensive. So what they do instead is they say, well, if the RAM could actually produce 32-bit words, That's fine for simple dual port. That's actually the most important RAM mode. And we'll build enough routing ports for that. But for true dual port, we'll just say you can't do it. Okay, the RAM itself could do it, but we're not going to give you enough routing ports. But we have this configurable width circuitry, so we'll just tell the CAD system the maximum width of this RAM in true dual port mode is only 16. It's not 32. And it's fine. So we lose a little bit of utility. Somebody who would have benefited from the widest words and true dual port just can't do it, but we save a whole bunch of area. And that trade-off is actually pretty good. We lost a use case that wasn't that important, and we saved a bunch of area. Does that make sense? And that's where that restriction comes from. Again, in lab 3, you'll see there's a restriction of if you're in true dual port mode, you can't use the full width of your RAM. You can only use it in kind of half of its maximum width, and it's coming from this constraint. You don't want to build all those routing ports. So your CAD system, which you guys are writing, has to enforce that. Does that make sense? Okay. So that's it kind of for block RAM. That's kind of your menu of trade-offs. But another thing that you could do is we could try to reuse the RAMs that are our LUTs. A lookup table is it's a ROM, right? It is a read-only memory. So, and a 6-LUT, it's not a huge memory, but it's actually significantly bigger than a 4-LUT. So with 4 LUTs, it was kind of tempting. Could we maybe reuse those lookup tables as RAM? And when you went to 6 LUTs, it actually got more tempting still because it's just bigger, right? There's more memory in there. So what we need, we can already read it, right? That's what you're actually doing whenever you're using a lookup table. You're reading out a truth table to implement a logic function, but that is actually just a read. So, but what we need to do is be able to write it. For normal lookup table use, the lookup table is written when you actually program the device. And that's done with special circuitry. It's kind of like a big shift register and a special write circuitry. We can't use that if we just want to write to one lookup table, which is what we need if we want to use this as a RAM. Like we can't reuse the configuration circuitry because we can't just start reconfiguring the whole design because it'll go crazy. So we're going to have to add something to it. And the question is it worthwhile or not? Okay, so it's going to depend on what we have to add. If we had to add a lot, then probably not. If we have to add a little, then probably it's good. So let's see what we've got so far. So here's a 6 LUT. We send in 6 inputs, and I'm going to now label those as just read address, okay, because that's what it is. And I get out 1 bit of data, my read data. And actual fracturable 6 LUTs are kind of nice because they can do this. But it can also say, well, let's use it in its fractured mode, in which case I get twice as many data bits because each of the 2 5 LUTs produces a data out. And I just lose some of my words, right? So I have 5 address bits now instead of 6, so 32 words instead of 64, but my words get twice as wide. So a fracturable 6 LUT actually has a little bit of width configurability, which is kind of nice. Let's see. So yeah, we have all this already. Nothing I've shown you here is any extra cost. We do have to add some write circuitry, though. Okay, so what do we need for the write circuitry? So for the write circuitry, well, we're going to need a write address. We'd actually really like this thing to work in simple dual port mode. So ideally, because FIFOs are like the #1 most important kind of RAM that you put in an FPGA. So we'd like to have a separate write address. And if we want to write to any one of the entries in a 6 LUT, that has to be 6 bits. And we'll need 1 bit of data. What is the thing we're writing? When we use it in fractured mode, we only need 5 bits because there's just 32 choices. But we're going to need 2 bits of data. Okay? So if you think about what do we need, we already have 6 bits of read address. Those are our LUT inputs in the 6 LUT mode. We just added 6 bits of write address, and we added 1 bit of what is the actual thing I'm writing, and that is 13 routing ports. Okay, Xilinx builds 6 routing ports for a 6 LUT, and Altera builds, or Intel builds 8. Okay, so 13 is a lot more, and every routing port means a whole bunch of muxing and routing, programmable routing, etc. So that's expensive. So this is going to be really expensive. To go from 6 or 8 to 13 is going to be prohibitive. We could check the same thing for what if we just use it in 5-LUT mode, like fractured mode. It's not much different. 5 read addresses, 5 write addresses, 2 write data inputs. We need 12 routing ports. We only have 6 in Xilinx, 8 in Intel. Doesn't look good. Okay, so yeah, it doesn't look like a good choice, yet both Xilinx and Intel actually have LUT RAM. So what did they do? Am I just an idiot and I can't count, or I lied to you? Routing ports are actually free. What do you think? Yeah, so that's a great answer. I'm just going to repeat that. So what I've shown you is kind of a straightforward way to do this, but it's not the smartest way to do it. It would give me the ability to turn every individual LUT into a RAM. But that's probably overkill. Not that many people need such tiny RAMs. I can instead think about turning a whole logic block into a RAM. And if I do that, I can basically share the write address signals. I can say, well, I'll write to all the LUTs the same location in every single LUT based on this write address. And so it's another example of how a logic block can help you by kind of creating a hierarchy where you can share signals. And that's exactly what they do. Okay, so Intel converts the whole logic block. So they say that the write circuitry has to be shared by all the ALMs, just like they share clocks and clock enables and so on. If they do that, they still each need their own write data input. Okay, they're not all writing the same bit into their storage, so you still need one input per 5-LUT or 6-LUT. So that's 10 inputs though, if I have 10 6-LUTs. And then I also need to have, I need to have a write address. So let's say I'm doing the 6-LUT mode. I need 6 bits for that, but I'm going to do that just once for the whole logic blocks. So what I can do is basically the ALM, I have my 6 inputs that I'm going to use for the read address, and I'm going to have 1 bit for my write data that comes in, and I'm going to steal the last routing port to get 1 bit of the write address. And I can do that. I actually have 10 ALMs, so it's not a problem to steal 6 of these from 6 ALMs and get my whole write address data. If I do the same analysis for what about 5-LUT mode, I now only need 5 inputs for read, per lookup table, and I need 2 write data inputs because I can write to both 5-LUTs in the same cycle, and I still have 1 extra input unused, so I'll steal that for my write address. So in both cases, it kind of works, right? I don't need to add any extra routing ports to the ALM. I don't need to add any extra inputs to the logic block. So now it becomes much cheaper. I just have to add, I do have to add the actual writing circuitry, so it's not free, but it's a lot cheaper. Does that make sense? And the constraint that I have is just now I need to write all of these LUTs as a unit. So I can only turn the whole logic block into RAM or leave it as logic. That's not a huge restriction because most people want RAMs that are not super tiny. So saying that you have to make RAMs that are 10 or 20 bits wide at least is not a huge restriction. I can still make 4-bit wide RAMs and so on. It's just I'll waste some of my logic block. Is everybody with me on this? Does this make sense? And so that's why I gave you in Lab 3 the estimate of a logic block that supports LUT RAM takes 15% more area. And that's again a reasonable number. That's actually what we found for some of the Altera devices that I was part of designing. It was about a 15% penalty. So not catastrophic, but not nothing. Let's see. This, I think I basically just kind of told you this. Okay, so I kind of just went through all of this, so I'm not going to say that again. How good is it? It's about 30 times more efficient than using registers. if you used all of the RAM in here, which is 640 bits. So there's a fairly significant upside versus using registers. It's not as efficient for big RAMs as a RAM block, but for small RAMs, it's pretty good. Okay, so what does Xilinx do? So Xilinx is pretty similar. So they're ultra-scale architectures, and later they basically have, okay, so what Xilinx does is they build just 6 routing ports for their 6 LUT. And then they have, let's see, let me think about this for a second. Okay, so they only build 7 routing ports. They actually build 6 routing ports for their 6 LUT, and then they give 1 extra one for the register. So they wind up with 7 routing ports, whereas Intel had 8. So if you look at that, in 6 LUT mode, they've got 6 of them used for read. They could use the 7th for the data to write to that. In 5 LUT mode, they'd have 5 of them used for read, and they'd have 2 left for the data inputs they need to write to the 2 5 LUTs. But there's nothing left for the write address, okay? Because they only had 7 routing ports instead of 8. They can't steal 1 from each thing and build up a write address. So any idea? They do work around this. Any idea what they did? So they could just add 1 more routing port, but they don't want to do that because they've got 7. They like 7. 8 is more expensive. What do you think they'd do instead? So they do share it across the whole logic block, so they use the same trick, but they've got to find a way to kind of get enough routing ports. They got none left per LUT, basically. Okay, so what they do is, I think, kind of clever. Okay, so if it's single read-write port, maybe this is what you were actually saying. So if they're actually doing single, sorry, I didn't fully understand what you're saying. So actually, you got the right answer for this. One of the things they do is if it's a single read-write port, so single port RAM, they just can basically use this read address as the write address as well. Okay, so that case works. And their logic block has 8 of these fracturable 6 LUTs. So it means they could do a 64 by 8 RAM, or they could do a 32 by 16 RAM. But single port RAM is not the most important application. Simple dual port was the most important, the most common. So what they do to make simple dual port work is they basically steal all of the inputs from one LUT. They go, okay, it'd be nice if we could use all our lookup tables as LUT RAM, but being able to they'll take one of their 8 LUTs, steal all of its inputs, so it can't use this RAM because it no longer has anything. Basically, you've connected up the write signals to its read logic, so you can't use it anymore. But it still works pretty well. So they lose one of their LUTs. They can still do, whoops, let's see if we can get rid of that. They can still do a 64 word by 7-bit wide LUT RAM, or they can do if they use it in 5 LUT mode, they can do 32 word by 14-bit. So they lose 1/8 of the theoretical capacity, but they avoided adding routing ports, so it's, again, a pretty clever solution. Does that make sense? Okay. Okay, so that's kind of the building blocks. So in Lab 3, you're working with a memory architecture that's very similar to Stratix 4. So that's Altera's 40-nanometer chip. So what does that architecture look like? It had 50% of the logic blocks support LUT RAM. Why 50%? Because nobody's going to buy an FPGA, which is a fairly expensive device, and turn all of the logic into memory. Because if they did that, well, they should probably go buy a memory chip, right? It'd be a lot cheaper. So maybe there are a few people who might turn 75% into RAM, but not that many. So because it's costing about 15% more area to add that write circuitry in, if you're pretty sure not many people are going to use more than half their logic that way, then just putting it in half the logic blocks amortizes the cost. So that's what they did. It does mean they have to lay out 2 different versions of the logic block. So you have some columns with write circuitry and some columns without. So it does actually make the FPGA a little harder to design, but it does save some area. And they put in 2 different sizes of block RAMs. So 9 kilobit and 144 kilobit. And it's basically trying to span that trade-off of the bigger block RAMs get you more efficiency per bit, but the smaller block RAMs are more flexible. You generally get more bandwidth out of them. You can also support just many uses. So if you need a lot of different RAMs or you need a lot of really wide words, these are going to be better. If you just need a lot of bits, these are going to be better. So in this chip, Altera just chose to build some of each, saying hopefully that makes everybody happy. Okay, so let's go through a few examples of like how efficient are those. Yeah. Yeah.
Just make it more, we'll have to use more LED lamps instead of just using one VRAM. Which one should we go for?
Yeah, it's hard to give a perfect answer. So if you were close to the capacity of this, and close probably means, you know, even a half, a quarter, then probably you're better off using the bigger RAM. It's going to be more efficient than building it out of a bunch of LUT RAMs. So from a silicon area point of view, that's probably around where the trade-off is. Even if you only use about, you know, maybe a quarter of that, probably still a better option. Once you get down to I'm only using an eighth or a tenth, the LUT RAM probably becomes a better option. But there's another piece of it. There's another piece of it of if you need really wide width, so you don't need much depth, LUT RAM's pretty good because basically, if you need really wide width, you might find that you're only using a small fraction of this RAM, maybe an eighth or less. So that moves you towards LUT RAM. The other factor is just what are you running out of? So the other nice thing about LUT RAM is if you're running out of block RAM, you can, and you don't need all the logic that's in the device, you can start converting some of the logic into LUT RAM. So a block that can be used for two things is always kind of easier to use than something that can only be used for one. Does that make sense? So there's kind of two aspects of efficiency. What takes less silicon area? That's one part of it. But there's another part of it of what's left given what your design is currently using. And even if you had a lot of RAMs, logical RAMs that fit very well to this 9 kilobit RAM, you might find, well, I've now used them all, right? And I'd have to buy a bigger chip. But maybe some of my logical RAMs, they're not bad in LUT RAM. Maybe they're not the best, but I've still got some logic left, so let's do that. Does that make sense? So there's kind of two pieces of the decision. Okay, so let's just kind of look at a little bit of relative, like some numbers on how big are these different physical RAMs. So let's consider that we want to build a logical RAM that is 2,048 words and 72 bits wide, and it's a simple dual port, one read, one write. So maybe this is a pretty big FIFO. And I chose that so it perfectly fits that big Stratix RAM, M144K. So we expect this to get by far the best results in that because it's a perfect fit to it. Okay, so if we map it to different options, one of the nice things about Stratix 4 is actually the area numbers of the blocks are public. Okay, so it was published. I published it in a paper that I co-authored. So, and most of the block areas are not public for FPGAs. So it's kind of nice to do things with Stratix 4 because we can actually say what it is in silicon area. So if I take this RAM, it maps to exactly one of those big block RAMs because it's a perfect fit. And the area, it turns out that takes 0.22 square millimeters, and it runs at 336 megahertz. Okay, so I could also take that same RAM and I could map it to 9 kilobit RAMs, and it actually needs 18 of them. And it needs 18 of them, and I don't need any extra logic because I'm just going to put them in a fairly deep and narrow mode. They each provide 4 bits of data, and I just put a bunch of them in parallel. So no extra logic. The area gets about twice as big. Okay, so almost twice the area. It actually runs faster. Okay, and that might seem surprising, but smaller RAMs actually do run faster because their bit lines are shorter, their decoders are smaller. And in this case, I didn't need any logic afterwards. I'm just taking a bunch of RAMs and putting them in parallel. So it actually runs faster. If I put it in LUT RAM, okay, so I need a couple of different things. A LUT RAM can't build 2,048 words. It can only build 64 words. So I'm going to need a whole bunch of LUT RAMs to give me my storage. I'm going to need a whole bunch of muxing and decoding in my logic as well. So this adds all that up. And it's pretty big. It's about 13 times bigger, and it runs relatively slow, about 40% of the speed, because of all that extra muxing and so on. And I could build it right out of registers. Okay, so build out of registers, build all the decoders, all the muxing out of logic. It's 313 times bigger, and it actually runs at about 40% of the speed as well. Okay, so this says big RAMs really are quite a bit more efficient in a physically large RAM, although they're not terrible in a medium-sized RAM. That's not a terrible result. They're pretty inefficient in LUT RAM and terrible in registers. Okay, so but you don't want to stop. I don't want to stop with this, because if you say, well, that's the only RAM, logical RAM anybody implements, I'll just 144 is the magic answer, build that. People build all sorts of things in their designs. So let's take another example where I have a much smaller RAM. So 1,024 words and 8 bits wide, and again, simple dual port mode. Okay, so this one, it'll take one of those big RAMs again, but it's wasting most of it. And so it takes the same area. It's actually a perfect match, or almost perfect match, to one of these 9 kilobit RAMs. And it's about 10 times smaller. Okay, so for this small RAM, that large physical RAM was pretty wasteful. And if I put it in LUT RAM, it's actually better than putting it in the big RAM, 0.83x of that, but it's about 8 times bigger than using the middle RAM. Okay, so, and if I go and put in even smaller RAMs, there actually is a point where the LUT RAM is going to win. Does that make sense? So yeah, there's no, because all these cases are reasonable use cases. Logical RAMs of all these sizes exist. That's what makes it hard to pick what's the best physical RAM size. So these are actually experiments from Stratix 5. So this is from the Stratix 5 paper. And they're very similar to some of the experiments that you're going to do in Lab 3. So what I'm showing here is area, okay? Area of the whole core. So don't include the IOs, but include the RAMs and the logic and the routing. And on the x-axis is basically how many logic blocks do I have per RAM block? Okay, so if I have, over here I have a very RAM-rich architecture. Every 5th column is RAM, or I guess every 6th column is RAM, right? 5 columns of logic, 1 column of RAM. Out here is a very RAM-poor architecture. 21 columns of logic, 1 column of RAM. And then there are various curves here. So this curve is basically very similar to Stratix 4. Okay, so you build one 10 kilobit RAM block, and then you build a smaller number of large 144 kilobit RAM blocks. And this is showing that if you kind of choose how many RAM blocks per logic block, you get a certain area, and it's about the minimum. If we make our small RAM block bigger, we made it 20 kilobits instead, we get this curve, and it's not as good. Okay, so this is saying 20 kilobits plus a really big RAM, not as good a choice as 8 kilobit or 10 kilobits plus a really big RAM. And then there are 2 options here where we say, well, do we really need to have 2 different kinds of block RAM? Because it's more complicated to lay out, it's more complicated for the CAD tools, so maybe we could get by with 1. So if we do 20 kilobits, it actually works pretty well. So this pink line shows that a 20 kilobit RAM by itself is about as good as this mix of 10 kilobit and 144 kilobit. And it's a bit simpler. So that's actually what Stratix 5 did. This curve says, well, what if we build 40 kilobits? And it's too big. All right, 40 kilobits was relatively inefficient. Does that make sense? Okay, so that's how we get, basically this is the Stratix 4 and Stratix 5 architectures are right around there. Let's see. I mean, the other reason you go, what, 20 kilobits? Why? First, 9 seemed kind of weird. Like, why didn't you use 8 but use 9 instead? And now instead of like 18, you're using 20. Like, why the weird numbers? It's basically for parity bits is why a lot of FPGAs use things like 9 kilobit RAMs or 18 kilobit RAMs instead of powers of 2. It's to have, often people are storing parity bits in the communication industry. So those extra odd numbers can be good for that. The reason these ones are multiples of 10 is they're actually allowing not just parity bits, but also error correction. And it turns out to do that, you need to, word widths that are multiples of 10 are kind of natural. it doesn't matter that much because most logical RAMs need a bunch of block RAMs anyway. So there's already this transformation from what the person asked for to physical RAM, so it doesn't make that much difference. Okay, so this is an overall slide that just shows the evolution for Intel's block RAM architecture. Before 1995, FPGAs actually didn't have block RAM. So the very first FPGA with block RAM came in 1995 from Altera, and it had really small block RAMs, 2 kilobits. But that still seemed really big compared to using registers or LUT RAM. And then gradually, as we go through, basically we're going through time here. Like this is the size of the device, but obviously that was increasing with time. So this is also time. We went to basically a mix of really small, 512 bits. Actually, this is 3 different RAMs. So we basically had 3 different sizes of RAMs there, so small, medium, and large. Then went to 2 sizes of RAM here, which is like Strat X4. Then 1 size of RAM, 20 kilobits. So in the case of Altera, they've kind of gradually gone to a smaller number of different block RAMs to simplify things. And they've also gradually been increasing the amount of logic per lookup table. So this graph is not like the total amount of, or sorry, they've been increasing the amount of RAM per lookup table. So this is not a graph of total RAM, which is going up exponentially. It's a graph of how many memory bits we have per logic element, right? So like lookup table. And you can see that the architectures are actually getting quite a bit more memory rich, so about 10 times more memory rich. So as systems get bigger, memory seems to be getting more important. Does that make sense? Okay, so let's talk about Xilinx. So mostly similar. Okay, so everything I talked about for RAM architecture is pretty similar for them. But they use their workhorse RAM as an 18 kilobit RAM, which is pretty close to 20 kilobits. So it's not a huge difference. It's also configurable. So you can use it as 18,000 words by 1 bit wide, up to 512 words by 36 bits wide. So it still has that programmable muxing. They also do the same trick where true dual port, they don't allow the widest width in order to save routing ports. They do something differently in that they actually build some extra hard circuitry, so some extra muxes that allow you to combine 2 RAMs together, basically do that decoding and muxing that you're doing in Lab 3 with logic elements. They can do that with hard muxes, which are smaller. So they consider that case, I guess, common enough that they actually put in hard logic to do it. But if you need more than 2, so you need to go beyond a 36 kilobit RAM, then you have to use soft logic, just like Intel. Okay, so Intel has been kind of gradually reducing the number of types of block RAMs. So they had 3 in one architecture, then 2, now down to 1. Xilinx has actually been going the other way. So in their most recent chips, they've added in really big RAMs, 288 kilobit RAMs. And those ones, they probably bought the RAM design from, designing large RAMs is kind of tricky for all the circuit reasons I talked about. So sometimes you go buy them from an ASIC vendor. So I'm guessing that they actually bought this one because it doesn't have width configurability. It's just 72-bit wide words no matter what. But Intel and Xilinx kind of went in opposite directions. Intel's been gradually like saying we want one kind of block RAM, and Xilinx has gone, we had one, now we want 2. I'm not going to show the graph, but the trend I showed for Intel is also true for Xilinx. They are also gradually increasing the amount of memory relative to logic in their devices. Okay, any questions on that? All good? Okay, further reading, so things I'm not going to talk about, but you might find interesting. So in Lab 3, you're doing a RAM mapper, and you're doing it to minimize area, which is what most RAM mappers do. But if you actually want to minimize power, you map the RAMs a bit differently, from logical RAM to physical RAM, because you're trying to minimize how many physical RAM blocks get activated on any given clock cycle. And it turns out that if you map your RAM somewhat differently, you can reduce that, but it does cost you some area and sometimes some speed. This is another paper that says we're getting more and more RAM on FPGAs, and SRAM is not that dense. Okay, it takes 6 or 8 transistors per bit. There are other memory technologies that can use 1 or 2 transistors per bit. And this paper looks at one of them, a magnetic tunnel junction technology, to see could you make FPGA block RAMs out of it. And basically the answer is you could, and you get about 3 times the density for large RAMs, which is good. But you'd have a slower write speed, which for FIFOs is probably going to be an issue. So I was involved in this paper. I think it's an interesting paper, and it talks a lot about the low-level circuitry of RAMs, if you're interested in that. Although ultimately I'd say the slower write speed means this is probably not a great idea to do. And there's another challenge, which is that FPGAs tend to be in advanced process nodes. So anything that you do that's not standard, you integrate some new memory technology and it needs a custom process, is also an issue because you want to be on the latest process, and usually anything that you change is going to inhibit that. I guess I'll show you one thing. What is a magnetic tunnel junction? It's basically this complicated material sandwich that actually fits in the metal stack. So that's what makes this really small. You basically get rid of that whole cross-coupled inverter and you replace it with a little piece of sandwich of materials that you actually put between 2 metal layers. And what you're left with are just basically the access transistors. So you can get a much smaller cell, but as I said, you get some fairly significant trade-offs too. Okay, so that's it for RAM blocks. Any questions on any of that? Okay, in that case, let's take a break till 5:32. Uh, broad expectations, read about 10 papers and briefly survey some area. There are a whole bunch of ideas for areas in there. It's not exhaustive. You can come up with your own. If you're worried, well, what if this is not a good area? You can ask me, and I'll give you my opinion. But I'm not very picky about area, right? Pick something that is relevant to your research or your interests. Doesn't have to be on my list if you don't want to take one of those. Some of these papers could be ones that we read. Shouldn't make a research topic which is like papers I read in ECE 1756 and take the first 10 papers right from that were assigned readings. Okay, don't do that, but can be some overlap. Generally, the best practice is to pick some subset of those, like 2 to 4 is probably a good number, and kind of dive deeper. So usually you summarize, here's kind of the landscape. Here's a bunch of papers I can group into these categories. I can see these contrasting approaches or these trends. And now I'll pick 2 to 4 of them that I find particularly interesting or particularly good contrasts and kind of dive into them more. If you try to cover all 10 in equal detail, you usually wind up with a kind of superficial treatment, right? So it's usually better to kind of do 2 levels of detail. One of the key things is I want to see comparisons, contrasts, contrast between them. Your thoughts. Is this the right approach? Are people missing something? What should they do next? Or what was great about this? To get you away, like, well, that actually shows like the voice of the author, right? Like you've interpreted these, you've synthesized them into something interesting. A very poor job of that would be I've got 10 abstracts, somewhat reworded, and I just go through them. Here's like paper 1, here's paper 2, here's paper 3. That would be, very poor analysis. So don't do that. Maximum of 3,000 words. Should have figures or tables. So if you get 3,000 words and you go, I have no drawings, that's going to be kind of hard to read. Those figures and tables can come from the papers, obviously. You just put a citation in the figure caption or the table caption to show you took it from that paper. It's totally fine. You can screenshot it. Sometimes people come up with their own figures, their own tables, which can be really good. If you say, well, I want to compare these 3 papers on these 4 key metrics that I think I can extract from them, that can be a very nice thing. You're writing it in LaTeX, which is a good experience for how do you write research papers. So once you really want to control the formatting of things, Microsoft Word becomes very painful. So someone asked, actually, do you have to use LaTeX? I guess if you write it in Word and the PDF is indistinguishable or close enough, I'll never know, but it is a good thing to actually learn LaTeX. The last paper I wrote with Microsoft Word was, I don't know, more than 20 years ago, I think, and I basically just gave up on where to put certain figures, like Microsoft Word just won. I was like, I don't really want this here, but I give up. I cannot figure it out. It's now taking longer than the research took to try to make Word put this there. So the good thing about LaTeX is you can always make it obey you if you find the right command. Any questions on that? It's all pretty clear? I think you'll have a less stressful holiday if you do not leave this till like December 18th, but I will leave it to you. I guess one other thing I will say is so I think it's actually good to just get it done. Some people have asked me, well, I got exams right up to then. I'm stressed out. Can I submit it somewhat later? Yeah, I'm going to be pretty relaxed on that. But I also don't want to kind of encourage everybody to just. It's good to actually finish things and have a break. Okay, so I think that's your best approach, and you can definitely do that. But if you're getting stressed out and you're saying, I'd really love to have a little more time, I'm basically going to give it to you. Okay, so that's fine too. Yeah. I'm sorry, I'm having trouble hearing that? Yeah, there's a lab 4. It's not as hard. Okay, so if you're kind of going, wait a second, what about lab 4? There is a lab 4, but it's just, you don't have to write any CAD tools. You don't have to design any hardware. You have to run a CAD tool and kind of do investigations of architecture trends. So there is a 4th one, but it won't take you probably nearly as long as some of the other ones did. Yeah, it'll be like December 13th or so. That one I'm going to assign right after we're done with assignment 3. Does that make sense? Okay, assignment 2 contest. So remember, this is like how much throughput in terms of convolution can you get out of an FPGA? So honorable mentions. This means you didn't quite win, but you had a very good solution. So Gang Yang, Siwei He, Bao Xinyang, Nafis Habab. I apologize if I mispronounced your name. So, and you guys were all in a relatively tight range of 2.7 to 3.4 gigaops per second, which is all very good. And then the absolute top performance, there was actually 3 people who were just close enough, so I called it a tie, all approximately 4.7 gigaops per second. So Jackson, Li Chen, and Kaifeng. And you basically did all the optimizations. So you pipelined it enough and used the DSP block modes in a clever enough way that you got to 550 megahertz, which you were limited by the DSP block's maximum clock frequency. So Intel just said, you're done, stop optimizing. Use symmetry. So the filters you were given are symmetric, which means that you can convert some multiplications to additions before you do the multiplication. And all three of these solutions did that so that they could basically not run out of DSP blocks as fast. And then they used the DSP features cleverly and block RAMs to build their FIFOs and buffers so that they didn't run out of logic, so that the limit was basically how many multipliers could they get in. So well done. So I'm going to give you a round of applause. And hopefully you're here. So I promised Amazon gift cards, so you can buy something courtesy of Jeff Bezos. So it was like, at worst, the world's second most annoying billionaire. So Elon Musk has moved into a category by himself. So are any of the winners actually here? Okay, so come on down and grab this. So. Hey, yeah. Congratulations.
Thank you.
And Jackson? So I'm terrible with names. I know was introduced before. Congratulations. Okay. So there's a speed component as well, right? There you go. Congratulations. So yeah, nice job. Okay, so we had background reading last week. I'll assign more reading this week. So the reading's moving into routing architecture, even though I haven't quite got there with lectures. I'm slightly behind, but it's fine, right? There's no exam, so it doesn't really matter. So, okay, so we got a few more things to talk about for blocks. We talked about logic blocks, we talked about RAM blocks. Now I want to talk about other kinds of function blocks. Multipliers being the most important ones, and then a bit about other hard blocks. Okay, so how do I, in general, evaluate, let me check the chat actually to see if there's anything I should be doing. Okay, so question, when will lab 4 be assigned and due? I mean, I can assign it any time. So would people prefer that I assign it now so you can kind of see it? Who would prefer to be assigned now versus like in 6 or 8 days? I guess that's close enough. Okay, a few. So I'll try to get it out in the next few days then. And it'll be due around December 13th. Again, I'm being a little lenient on if it reduces your stress level to kind of say, like, could I have a little extra time? That's fine, right? Part of the due dates is frankly just to space things out. So, okay, so we've looked at some logic blocks and RAM blocks. In general, this is the procedure by which people evaluate, should I harden some important function? And the example I'm using is PCI Express. So PCI Express, if you go back to older FPGAs, was not hardened. Now it's hardened in all modern FPGAs. So the way you go about doing this, usually, is first, if it's an important enough application, you are going to develop some soft IP. Okay, so you want people to not have to build it from scratch. You want them to just take an IP core in your CAD system and instantiate it. So you build that for them. And that is going to be generally parameterized, meaning most things have many configuration parameters. And you put that in your IP so you can generate the right IP core for the right customer. So you have that, and you can build it into the soft fabric, and you can measure its area, power, and speed just using your CAD system. Now you're seeing enough people using this, you think maybe we should actually, in the next generation of the chip, we should harden this, put it in. So you take this soft IP, and you have to modify it to make configurable hard IP. What does that mean? Like, couldn't I just take the exact same IP? Well, once you're going to make something hard, soft IP is kind of nice. You can just say, if it's this, let's say it's PCI Express. If it's generation 1, generate this Verilog. If it's generation 2, generate this other Verilog. If it's generation 3, generate a third Verilog. Okay, hard IP, you can't do that, right? You actually are putting this block on the chip. It's in gates and in RAM and so on, and it can't be changed after that. So there's none of this, tell me what you want, and I'll generate the right Verilog. If it's not on the chip, it's not going to work. So usually what you have to do in this configurable hard IP is, well, all the options you want, you have to build. So let's say I had 3 generations of PCI Express I wanted to support. I'd build Verilog for all 3 of those. And then I build a few SRAM cells that allow me to mux between them. And now people can ask for any one of those 3 generations and it'll work. Sometimes you can get a little more clever. If you find that there's actually a lot of commonality between these, then maybe the common part I can build once and not mux it. So this would be the straightforward way to make your IP configurable, but sometimes you can be a little more clever. But I guess the key point is that you can't just take one instance of the soft IP and harden it and say that's my gain. You know, I just got my 20x or my 4x gain that we predicted. You know, 20x for logic, 4x for maybe lots of stuff that has RAM and so on in it. It's going to be different because you're going to have to actually put more in your hard logic to give yourself the appropriate amount of flexibility. Okay, so then you measure from that your area, your power, your speed, and you have to include the routing ports. So it's another thing that sometimes people forget. You know, they just worry about the function, but you got to actually hook this up to the programmable fabric or it's not going to be very useful in FPGA. And then now you basically have area, power, and speed of your hard and your soft version, and you got to estimate usage. Okay, so the soft version, if somebody doesn't use it, it costs them nothing. They just use the device to do other things. The hard version, somebody doesn't use it, it costs them the same in terms of area. So something that's used 90% of the time is going to be relatively easy to justify hardening. Something that's used 5% of the time is going to be extremely hard, right? Even if the gains are huge, for 95% of your customer base, it's just dead weight. And then you decide if it's a net win. Actually, so I have a question. Do you think power, okay, so historically, people evaluated to harden something or not, primarily based on area and somewhat on speed. But now they often also look at power. Power is more and more important. Do you think that power pushes you to harden things more or less or the same versus when you were looking mostly at area? So if you're going, you have no idea. It's one of those questions, you got a 33% chance. It's not bad, right? So you could just take a random shot. Everyone will think you're pretty confident anyway. If you just say it with confidence, you're already halfway there. So what do you think? Okay, so you think that, so you're kind of in the right ballpark. So by parasitics, you mean static power? Is that right?
Yes. Like you still probably need to, I guess, leave that hardened block programmed in a way that it doesn't disrupt the rest of it. So that's going to take some power to fire it out.
Yeah. So it's reasonable thoughts, but it actually works the other way. Okay. So for area, if somebody doesn't use it, the area is gone, right? So it's dead weight for everybody who doesn't use it. But it's a big win if you do use it, and it's much smaller than the soft logic. For power, dynamic power, it's a big win. Okay, it's actually relatively, it's to first order, the dynamic power win is proportional to the area win because you just have less capacitance. So if you use it, you get a big win. If you don't use it, you actually don't clock it. So you actually don't waste dynamic power when you don't use it, which is better than what you got for area. Now you still have static power, which is significant too. But for these hard blocks, like say PCI Express, if the static power is significant, you can put what's called a sleep transistor on it. So you put a high threshold voltage transistor that's very big between the whole block and the power rail. And you put the whole thing here, like PCIe. And by turning off this high threshold transistor, which will not leak much, right? That's why it's higher threshold. You basically cut the static power of this too. We don't usually use those cutoff transistors in the programmable fabric because they do have a speed impact, right? When I put an extra transistor like this in my path to power, and I put all my logic down here, there is some delta V across this, which means all the rest of my transistors are operating at slightly reduced, well, somewhat reduced voltage, which makes them somewhat slower. So, but for a hard block, that's not as bad. Hard blocks we can make pretty fast already compared to this programmable fabric. If they're 10 or 15% slower than they could have been, but they're still 3 times faster than the programmable fabric, you say that's pretty good. And this allows me to cut off their leakage power. And I don't clock them when I don't use them, so they also aren't going to take dynamic power. So, yeah, so the increasing importance of power makes you want to harden more stuff, as long as you put these sleep transistors on it so that it doesn't leak when you don't need it. Does that make sense? You still have to pay attention to area, though, so that doesn't mean you just go harden everything you want, because your cost will be terrible. Okay, so let's look at an important hard block example, DSP blocks. Okay, so one of the things I said there that people forget sometimes is remember the routing ports. So that's like you need to figure out if this thing is big enough and used enough that it's worth hardening. But you also have to think about, when I harden it, does it have so many routing ports that I didn't really gain anything anyway? So the way a multiplier works is basically the way you do pen and paper multiplication, right? So you take one operand is here, the other operand is essentially here, and every place where both of them have a 1, we just use an AND gate and we get a 1. Okay, so we get a whole bunch of partial products, and every partial product, as we move down this one, is shifted over by 1, which if you think about how you do, I have young daughters, so I've done this more recently than you maybe, but if you do multiplication with a pen and paper is what you're doing. You probably just don't do it in binary. So you get a whole bunch of AND gates, and then you got to add all these bits up. And so you got a whole bunch of adders. And that's basically that's basically how a multiplier works. There are a variety of little tweaks people can do about how they organize the adders, etc. But they're all basically doing this. And the amount of logic you need is proportional to n squared, where n is the bit width. Okay, so I have two n-bit inputs, and I produce an output. The amount of computation in a multiplier is n squared. So n rows times n columns. And we care about multiplications. Like the most important multiplication historically in FPGAs has been about 18 by 18, because that's about enough for wireless signal processing and filtering in that application. 18 is pretty big. So 18 squared is a pretty big number, so it's actually a fair amount of logic for an 18-bit multiplier. So that's good. It's also fairly common. People do a lot of multiplication, particularly in things like signal processing and nowadays in deep learning, and those are important applications. So it kind of checks both those boxes. Relatively big, relatively common. So we need to, but then we need to check routing ports. So if we have we're going to multiply two numbers for each n bit. We have 2n inputs. And then we produce an output, one output, which is twice as wide, so 2n outputs. As long as n's not too small, that means we have much more computation than inputs and outputs. So that's good, because it implies that probably making the computation more efficient is worthwhile, because we're not totally dominated by routing ports. Does that make sense? So it looks like a good candidate. And yeah, this is essentially the analysis that led to multipliers being hardened as new blocks in FPGAs. So this is an 18 by 18 multiplier, okay? And it's basically showing you all the partial products. So every one of these, basically I've got input A here, input B here, and I'm showing all the partial products, so AND gates. And then we're going to add all these things up, and we're going to produce an output down here, okay? So I've decided 18 by 18 is the most important multiplication size for our market, so I'm going to harden this. One of the things you want to do in an FPGA is think, well, is there anything I could do to make it more flexible? Because we're always trying to capture, make it more usable by more people. That makes the chip more efficient, gets larger markets. So is there anything that we could do to make this more flexible? Looks like a good 18 by 18 multiplier. Could we do anything else with it? And we obviously want to make it, we also don't want that to cost a lot. So we're always looking for how can we make it more flexible, like that width configurable multiplexing in a block RAM. It's pretty cheap, and a lot of people can use it. So that's good. So we're kind of looking for something like that. So any ideas? What could I do with this? Yeah, what do you think? Yeah, so there's nothing magic about 18 by 18. It's not like all multiplications have to be 18 by 18. Video processing doesn't need 18-bit precision. So you're saying, well, that kind of looks like we could chop it into smaller multiplies. And that's true. So if we actually change a little bit of this hard logic, basically if we stop the carries from propagating across this line, and if we stop them from propagating across that line, we wind up with 4 9 by 9 multipliers, okay? Because that's just what it is, right? Like we've got this big array of partial products we're adding up. If we stop them from going across these two lines, we naturally get 4 9x9 multipliers. It's not a lot of logic to do that. It's basically we throw a few extra AND gates or multiplexers in there on those lines. So it's going to be relatively cheap. And we get 4 times as many multipliers when we want to do 9x9 multiply. And 9 bits reasonably common. So it's been used in video processing for a long time. And now it's used in machine learning a lot. Okay, so it's become really common lately. So what do you think? Sounds good? We should do this? So anything that gives you concern about this? What do you think? Yeah, so what I've got here is 4 9x9 multipliers. Because with a little bit of extra circuitry, I could do 4. But maybe I shouldn't. So I'm not saying that I did that. When I say I mean the industry. So is there anything else I should worry about here? So it looks pretty good, and I didn't add much logic, and I got 4 times as many 9x9s. Anything I should worry about? So what's really expensive in FPGAs? So the routing ports. So how many inputs and outputs does this have? So it has, okay, so before I had 2 18-bit inputs, right? So 36 total inputs. Now I need to have 2 9-bit inputs, so 18, but I have 4 of those. So that's 72 inputs. If I do the analysis for the outputs, it's the same. So I doubled my number of input ports and output ports, and that's not cheap. Okay, so I could choose to do this, but if I choose to do this, I better believe 9-bit's really important. It may be as important or even more important than 18-bit, because this is going to actually cost me a lot of area. So what actually you'll find is that FPGA architectures that do this, and there are quite a few that do, even though they could make 4 9x9 multiplies out of this, they don't. Okay, they will basically say, let's just make 2. Maybe we'll not use this one, not use that one. We'll let you use 2 of them, and that still fits in our input and output budget. So we don't have to add any routing ports. It's cheap. But you only get kind of half as much as you thought you might. Does that make sense? Okay, so the original DSP blocks that went into FPGAs were put in by Xilinx, and they were just multipliers. Okay, but then people started thinking, well, there's a lot of the times when you're doing multiplication, there's some other stuff around it. Maybe we could harden that too. So let me give you a common example. So finite impulse response filters, which we've talked about before. So it's one-dimensional convolution, and it's used in signal processing all the time. And it's just basically take some stream of data. You've got the last n samples from some data stream, maybe a wireless base station, and you're going to multiply each of them by some coefficient in order to filter it, like put it through a low-pass filter, et cetera. A lot of filters are symmetric, where basically this coefficient might be 5, and the last coefficient is 5. And this coefficient is 4, and the second last coefficient is 4. So that's called a symmetric filter, when basically you look at it from the left side and the right side, and all the coefficients are the same. Not all filters are like that, but a lot are. If you have a symmetric filter, you can refactor it to basically reduce your number of multiplications by half by basically adding the signals that are going to get multiplied by the same coefficient, and then just doing the multiplication once. Okay, so this is a transformation that you can do to reduce multiplication when you're doing a symmetric FIR filter. Okay, so why am I telling you all this? Because it's a very important application for FPGAs. So if you look at recent DSP blocks, they're not just multipliers. Okay, so here's a hard multiplier. They actually include registers on their inputs. They include adders, so they can do multiply, accumulate, registers on their output, registers in between to make them go faster. And I've arranged, this basically is a Stratix 4 DSP block. That's what Stratix 4 can do. And we're using Stratix 4 again because we know the area of this block. It's been published. So all of that can actually fit inside of a DSP block, not just the multiplication. And the rest of this is to implement a symmetric FIR filter. So to do a symmetric FIR filter, I'm doing this trick of adding the first signal, or the first most recent value, and the oldest value, and then they get multiplied by the same coefficient, and I'm doing that for pairs, okay? So, and basically these are all registers. So I'm bringing in the inputs, delaying it through a chain of registers, adding together the pairs that are going to be multiplied by the same thing. This is called a systolic implementation. To make it fast, basically there are registers on the output path as well. And to make the pipelining work, that's done basically the way we did talked about in class, where you draw cut lines. To make the pipelining work, you actually have to add those registers on the input as well. This is why instead of having just a straight shift register, we have some extra registers. It's because basically, it's to basically line up the latency with these extra registers that were put in the output path for speed. So basically the modern DSP blocks are pretty good at doing things like FIR filtering. So as I said, this dashed line shows you what's in Stratix 4, and it allows you to build a nice systolic FIR filter without a whole lot of extra logic. In this case, it was symmetric, so I did get some extra logic for this adder and for all these registers. But the rest of it is all hard stuff. Does that make sense? Okay, so the reason I showed you that is because this is from the Principles in Practice paper. We can analyze, well, how efficient is it? Because we actually know what the area of those DSP blocks are. It's been published. So let's first take an asymmetric filter. So an asymmetric filter means we can't do this trick. Can't do this adder trick because every coefficient is different. So if I drew this, it would actually look a bit simpler. It's just a shift register and a whole bunch of multiplying accumulators. Okay, so for that case, if we use DSP blocks, and the DSP blocks are the Stratix 4 generation, we use almost 7 DSP blocks. The area's been published, so we know that takes about 0.6 square millimeters, and it runs at 510 megahertz. It runs really fast because it's deeply pipelined, and there's actually dedicated routing for these connections to go between the DSPs. If we just did this in soft logic, so we can build multipliers and adders and shift registers out of the logic, and if we did that, we don't use any DSP blocks, but we use a lot of fracturable sixlets. The area is about almost 4 times bigger, and the frequency is cut about in half. Okay, so there's a pretty significant gain from hardening this. And that's when the coefficients are fixed. So if the coefficients are fixed, it means they're known to the CAD tool. And the CAD tool will actually take that into account when it builds the multipliers. It'll actually get rid of some of the multiplier if it knows it's being multiplied by 0. Sometimes you can do that, sometimes you can't. If the coefficients are not fixed, they're actually being read out of a RAM or brought in from IOs or something, then it can't do those tricks. And the hard logic or the soft logic version is still bigger. Okay, so it's about 8 times bigger than the hard one and about 40% of the frequency. If we do this again for symmetric filters, it's a little closer, so still a big gain, a big win. Whoops. Let's see if I can get rid of that. That's interesting. Huh. I don't know if I want to. Okay, let's get rid of that. Okay. Sorry about that. Lost control of my tablet. Okay, so we do this again with symmetric filters. So again, those are the ones with the ability to do this pre-addition trick. Then the gains are a little bit less. Still 3x if we had fixed coefficients, and 6x if we didn't have fixed coefficients. They're a little bit less because we basically have more soft logic. The adders and registers, the pre-adders and registers were in soft logic in this case. Now the next generation after this of DSP blocks from Altera basically pulled in these adders. Okay, so the generation after that, they went, oh, these symmetric filters, we can make them even more efficient if we stick that in the DSP block, so they did that. It makes the DSP block a little bit bigger, but adders aren't that big, so they were able to do it, not add many routing ports, so it was still a net win. So these numbers are, the reason I'm showing these are also, they kind of are a useful check on some of the papers we looked at early on, what's the benefit of hardening. So they're in the ballpark, 4x to 8x. but notice they're not, they're not at like 20x. So it is difficult to get once you basically put a bit of configurability into a hard block, like a DSP, and you account for the fact that applications never use everything, you don't get to those 20x and 30x improvements that we saw earlier, where people said if you took logic and you just put it into gates, how much more dense is it? We never quite get that when we harden things, because we have to put some configurability back in, and nothing ever maps perfectly. But you can still get a lot, right? We're getting 6x, 8x area gains in a lot of cases, and that's pretty good. Yeah?
So at the beginning you mentioned soft fabric. You mean the logic?
Yeah, soft fabric just means like lookup tables, and it just means like the logic blocks and the programmable routing. So, okay, so this is a very busy slide from that paper, but kind of highlights in one diagram how have DSP blocks evolved. So the very first ones were in Xilinx's Vertex 2, and they were just 18 by 18 multipliers. Then Altera basically made a more flexible DSP block that used the trick of being able to break up the 18 by 18 multipliers into multiple 9 by 9s. They actually also could combine multiple 18 by 18s into one bigger 36 by 36. Then, let's see, I don't want to talk about that one. DSP blocks for FPGAs for many years only did fixed point, so integer. Integer and fixed point is the same hardware. You just keep track of where your decimal point is. ARIA 10 from Altera is the first one that added in floating point. So it could do either integer or it could do a floating point 32. And there's a paper on that that shows how they did it without costing too much area. For many years, there was a feeling in the FPGA community that, you know what, if you work hard enough, you can always do it in fixed point, right? In floating point, you don't need that. That's for people who are kind of lazy. You keep track of where the decimal point is. And it's actually true. If you do, for things like signal processing, if you are careful enough, you can keep track of where the decimal point is, and you can do it in fixed point. But there are people who don't have time, right, to do it that carefully, check that they never get overflow, et cetera. So ARIA 10 was the first FPGA that just said, we give up, we put floating point units in. And it wasn't clear at first whether that was a good idea or not, but in subsequent years, other chips have followed in its footsteps, so it's become kind of clear, no, that really is the right thing to do. So, and it is interesting because in theory, you don't need it. You could just get by, but it's too hard to get people to design all their systems that way. Lots and lots of FPGA systems still use fixed point. It's probably still dominant, so I'm not saying that people don't use fixed point. It's just some applications are just not worth it, right? Like, I'm not going to buy enough chips. I don't want it to go to that level of optimization. Let's see. So basically, more and more Versal, basically, Xilinx's most recent chip, has not only FP32, but also floating point 16, which is important for machine learning. So you can do things in reduced precision machine learning, so they put that in. And then, so you kind of see more and more precisions going in. So each of the vendors is kind of using these tricks of how do we recombine these multiplier arrays to make different combinations. And then this chip is a bit different. So a recent chip from Intel, and it has a lot of multipliers. So 38 by 8 multipliers, or you could do 64 by 4, which is a lot more than any of these other ones. You can see this one was like, it could do, you know, 1 27 by 27, or 2 18 by 18, or 4 9 by 9. So I could split 4 9 by 9 into 8 4 by 4s, but this is a lot more than that. This is like 64 by 4s, and, you know, 38 by 8. So that's kind of different. So let's look at what that one is. Okay, so I guess, what are the trends? So more fracturability over time. First ones were just 18 by 18. Then over time, people added floating point. You could split the 18s into 9s. Now you can even split them sometimes into 4s. So adding some flexibility back in. The blocks themselves got more complicated, from just hardening the multiply to hardening multiply accumulate to hardening basically everything you needed for a FIR filter or dot product to floating point. And then this last one, as I said, is a little different. And this DSP block actually is targeted at deep learning. it's not actually it wouldn't be very good for wireless signal processing because it actually can't do, 18-bit fixed point. It can do 32-bit floating point, but it can't do that many, 18-bit fixed point, etc. So it's really targeted at deep learning. And let's talk about that one a little bit. So instead of getting, basically, Intel has a Stratix 10 device, and this Stratix 10 NX, which is a deep learning focused FPGA, is based off of it. So it's the same as any other Stratix 10, except they take out the DSP blocks, and they put in these things that are basically a different kind of DSP block that they call a tensor block. And a DSP block can do two 18-bit multipliers, one of these Stratix 10 DSP blocks. In essentially the same silicon area, this tensor block can do 30 8-bit integer multiplies or 60 4-bit. So part of that is that, well, small multipliers don't take as much area, right? The computation area grows quadratically. So I can split these 2 18-bit multiplies. I could split each of them into 4 8-bit. So 2 of them, I should get about 16. They actually got 30. So they took out some other logic, and they got even more multipliers. So they got 30. But their big challenge is inputs and outputs. Okay, so if I take these 2 18-bit multipliers, so I need 36 inputs for each of them, right? 2 times 18, and there are 2 of them. So I need 72 inputs. And then there are a few control signals, so I need a little more than that. If I take 38 int 8, okay, so I need 2 8-bit integers for each of them, so I need 16 bits times 30, which is, I think, 480. So that is a lot more inputs. And if I do the same calculation for the outputs, I get the same problem. So yet Intel says they fit this into approximately the same area. So they can't do that with this many inputs. This tensor block would be huge. So what they did is they're basically specializing it for deep learning. So they know that deep learning has certain data reuse patterns, and they're exploiting those. So the first thing they did is they arranged their multipliers not as 30 independent multipliers, but as 3 dot product units. So each dot product does 10 multiplies and accumulates the results and produces, 1 output. So that's how they solved their output problem. Okay, they don't have 30 outputs. They have 3 because they force you to use them as dot product units. Does it make sense? If you didn't want dot product, then don't buy this chip, right? Because it's not going to be very good at it. But that doesn't solve their input problem, right? So the dot products units would still need those 480 inputs. So what they do for the inputs is they basically put some registers in here. Each of these registers represents actually 10 registers going to this dot product unit. And they basically, you can preload these. You can preload them with a small number of inputs, or you can preload them with some dedicated routing from the previous tensor block. And they build 2 copies of them. So the idea is that you can load, they act as like essentially a ping pong buffer. You can preload 1 copy while the other one is actually feeding data into the dot product units. And again, there's not 3 registers there, there's 30, right? Each of those represents 10. And then the other input to the dot product units, they basically have enough inputs. They can use 80 inputs, and they could bring in 10 numbers, 10 8-bit numbers. They broadcast those to 3 dot product units each. So each of the 10 numbers feeds 1 entry in the dot product, but it doesn't do it in just 1 dot product unit. It feeds 3 of them. Does that make sense? So they do a mix of broadcast and reuse. This means that in the end, they only need about as many inputs and outputs as the old DSP block used. But they've got some significant restrictions on use. So the question is, will that work? And this animation in the top left is just showing the most common kind of convolution in a CNN for deep learning. And it's basically a filter moving across a 3D set of activations. So these are activations, and what's moving across it is a filter producing outputs. So I'm not going to go through all the details of this, but basically, you can see we use each of these numbers, each of these activations, many times. So by loading those activations into these registers, we can basically load them in through a limited number of inputs over many cycles as a shift register, while computation is happening from the other set of registers. And we can use them several times, because those activations get used over and over again. And then it also turns out that we use each of these activations gets multiplied by each of the weights that we bring in is not going to multiply just one activation. You see the weights are kind of gradually scanning across the activations. So we can actually broadcast the weights. So the weights come in here, get broadcast to, so 10 weights get broadcast to 30 multipliers. And we basically are adding up data as we scan across all of these activations. So we don't actually need to bring out all of these intermediate results. It's okay to just keep accumulating and bring out a limited number of results. So it turns out that, yeah, you can map deep learning applications to this efficiently, although it is non-trivial. So basically, it takes a fair amount of re-architecting of the hardware to make that work. The results are on two different accelerators. So ones that we talked about a few weeks ago, HPipe and the NPU. Depending on the neural network, they get from about 3x to 6x performance gain by using these tensor blocks, which is pretty good, okay, given that they take about the same area as a DSP block. It is less than the 15x maximum, right? These have 30 multipliers. The conventional DSP had 2. So in theory, you'd go, well, maybe I could get 15 times the performance. They don't, because these restrictions do matter. You do lose some efficiency as you're loading things up and trying to structure them into dot products, et cetera. But it's still a pretty big gain. Does that make sense? So it's kind of like the next stage of how do I save input ports. This is restructure your computations to keep some of your data local inside the block for a while, and other data must be forced to be broadcast. So you really have to take that into account as you're structuring how everything works. But you can get a big gain by doing it. Okay. Okay, so that was hard block example 1. I only have, I think, one other example. And I think routing architecture we may not get to today. Okay, so PCI Express. I told you that PCI Express, I used it as an example earlier. So this is what PCI Express looks like. It's actually multiple levels in the protocol. So the first thing is the PMA, which I think stands for Physical Medium Attachment. And basically, PCI Express brings in differential data. Okay, so you have a plus and a minus I/O. And the very first thing to do is they go into a differential amplifier to detect what did you get. So at high speeds, usually you have to go differential and use two signals, especially if they're going a long distance. So PCI Express does that. At the speeds PCI Express is running at, so many gigahertz, you can't align a clock to the data. You can't send a strobe or a clock alongside the data. So that's what DDR chips do. But DDR chips are intended to be pretty close to what's talking to them, and they don't cycle at as high a frequency. At these frequencies, you just can't send a strobe that's aligned with the center of your data window. So instead, you recover the clock from the data. So we basically, the encoding of PCI Express guarantees a certain amount of transitions. Like you'll never get an extremely long sequence of just zeros or ones. There will always be transitions. This clock recovery unit basically detects those transitions and adjusts the clock frequency and phase coming out of a PLL to make a clock that will be aligned with the center of the data valid window. Okay, that data's really fast, okay, depending on the PCI generation. The Gen 3 is 8.5 gigahertz. You can't send that to the programmable fabric. You can't actually do much with that. Not many things run at 8.5 gigahertz. So the next thing you do is you do a serial to parallel conversion. So you get a wider word, but you can run it slower. Okay, so this was all like high-speed analog, basically. After that, there's a bunch of digital logic called the physical coding something, sublayer. And this does a bunch of things. Like this, for example, is taking 10 bits of data and decoding it to get 8 bits of real data. Okay, so the way that PCI Express Gen 2 made sure that they didn't get that many, that they got a certain number of transitions. They took every 8 bits and they recoded them as 10. And they just forbade all combinations of bits that wouldn't have enough transitions. Okay, so this has to undo that. It takes 10 bits of data and turns it back into the 8 bits they really represent, and so on. And then there's basically some higher level protocols that happen, like actually figuring out what kind of data message is this from PCI Express and so on. So the protocol has multiple layers, from kind of the very high speed analog to just get the data, some high speed digital to remove the coding and do error correction and so on, and then some higher level protocol layers to decide what does this mean. And then after that, it sends it to the FPGA logic. The way this, and a bunch of these are optional. So people can say, I want to do this or I don't want to do this. There's quite a few variations of how people use this. So you get multiplexers in it. So that's what all these multiplexers are for. So you can do an operation or skip it. And in the hardened PCI Express that FPGAs do, they usually let you skip entire big blocks. Now you can't skip this. There's no way the soft logic can do that. But you could say I'm doing some custom variation of PCI Express, or maybe using the IOs only, but doing my own thing. You could skip all of the digital logic, or you might skip just the higher level protocol. So you get these bypass muxes. And basically going the other way is just the opposite. Okay, so all the operations run the other way. Okay, so should you build hard PCIe? So all modern FPGAs have it, so we know the answer is yes. But what was the decision process on it? Because it wasn't always hard. It was soft first. So the soft logic size is big. The protocol is relatively complicated. So if this part has to be hard, right? The part where you have that high speed analog signaling, like that just can't be done without some hard special purpose circuitry. But after that, I could choose to do the digital stuff and certainly the higher levels of the protocol and the soft logic. But it turns out the data sheet is pretty big. It costs tens of thousands of LUTs and flip-flops to build that. If you put it in standard cells, it does get about 20 times smaller. The hard logic is also faster. What that means is we have to go serial to parallel still, because we can't take something at 8.5 gigahertz through kind of much of anything. But we don't have to make it as wide. We could run it at maybe 500 megahertz instead of 250 in the soft logic. And that actually lets us use data paths that are half as wide. So that's actually a further area reduction if we can clock it faster. The protocol is fixed and it's widely used, so we're kind of pretty confident this is going to stay there. The cost, though, is that we do have to add a bunch of muxing. So I showed you all those bypass paths. You need a fair amount of configurability. You need to support all sorts of generations. So you're going to lose some of these gains by building more than any one soft logic would. But it's still a net win. Okay, so and that's why it's hardened. Also makes it easier for people to use, because you kind of guarantee that the timing is all going to work every single time. So that's also an important factor. So let's take PCIe Gen 3. And we'll take by 8. So by 8 means 8 lanes. So PCI Express, there are many flavors. So you have different generations, which each get faster. And then you can also do it wider or narrower. So I'm going to do Gen 3 and 8 lanes. So that means 8 differential pairs. Each of those 8 lanes is running at 8 gigabits per second, and they're full duplex, which means that you got wires going out, you got wires coming in. So you got 8 gigabits per second, or gigabytes per second, because I'm doing by 8. So I've got 8 of these bits, each of them at 8 gigahertz. And those are going in and out of the chip IOs. So depending on how good an FPGA designer you think you are, you're not going to be able to make your logic run at 8 gigahertz. Maybe you can make it run at 250, maybe 500. But those are probably your options. So let's just take 250. So I say I can make my logic work at 250. And it's talking to the output of this PCI Express block. So how do I link these things up? I got a block that wants to send me, initially had 8 gigahertz data, and 8 gigabytes per second is what's coming out of it. So how do I match these things? So on the one end, I've got 8 gigahertz and 8 bits. And I'm saying that I can handle maybe 250 megahertz in the fabric. Yeah?
Create the clock running at 250 megahertz. We have phase shift between the clock.
Okay, so I'll have a phase shift. So I do have to transfer from the 8 gigahertz to the 250. You're right. But I don't want to lose any data. Okay, so this 8 gigahertz clock is going to be sending me new data many times per 250 megahertz clock cycle. So how do I handle that? I don't want to lose any data. I don't want to just say I'll capture every 30-second piece of data or something.
Yeah, so like, for example, the input data is 500. And
Yeah.
your clock can only run 250.
Yeah.
You create 2 clocks. And the 2 clocks has like half cycle shift.
You could do that. Okay. I see. Okay, so you're basically telling me how to build like a serial to parallel converter, I think, right? You're saying capture it twice. Yeah. So that is the basic idea. So we need to do a serial to parallel conversion, and the logic you're describing will do that. Although I need to go a lot wider. So I'm not going to go from 8 gigahertz all the way down to 250, which means that I actually need to widen this by 32 times because I'm slowing the clock by 32 times. So instead of 8 bits, I'm going to wind up with 256 bits. Does that make sense? But I can still carry all the data. So that's what's done, right? So the last stages of this hard block are basically serial to parallel converters that let us present a wider but slower signal to the fabric that we can handle. But it does mean that this becomes quite wide. 256 inputs, 256 outputs for this block. The average logic block, so that looks kind of pretty different, right? We're hardening this block, and it's got 256 inputs, 256 outputs. The average logic block that we've been looking at, so let's say it's an Intel logic block, it's 10 fracturable sixlets. We saw that has typically around 30 inputs and about 20 outputs. Which is a lot less than 256 inputs, 256 outputs. If we just take that and we just connect it up to our routing fabric in one spot, just like we do for the logic block, we're going to have a big problem. And the reason is, remember our channel width is, we used this rule earlier. Our channel width has to be lambda, the number of used inputs for a block, times the average distance, r bar, that they had to travel, and then we can divide by 2, because some of them might be going horizontally and some vertically. But then we have to make our channels that big. Basically, this lambda for a logic block is about 30, and the lambda for this PCI Express block is about 256. So if we hook it up to just one of our routing channels, it's going to be a big problem. It's going to be a big routing hotspot. It doesn't behave the way the other logic blocks are. We'd have to make our channels a lot wider to support this. But you don't want to make your channels a lot wider because then they're going to be wider everywhere, and that's going to be overkill for the logic blocks. So what you do for a block like this is the number of signals it has essentially defines how large an area of routing channels it has to connect to. So you want to make it appear as if it was just a bunch of logic blocks. So if we take, we had 20 outputs per logic block. If we take these 256 outputs, divide by 20, it says we need to hook up to about 13 routing channels, or at least we need to hook up the same way 13 logic blocks would hook up. Does that make sense? So this is basically the PCI Express block. Has to be made to have a pretty big perimeter. If there's a lot of logic, that's not a problem. It's probably already pretty big, so it's got lots of perimeter. And we basically spread the signals, its inputs and outputs, out over basically many pieces of, many horizontal routing channels and many pieces of vertical routing channel. So it doesn't present a local routing hotspot. This is another constraint, basically, for hard blocks. If you have a lot of inputs and outputs, it kind of puts a minimum size or minimum perimeter on how do you hook up to the programmable routing. Does that make sense? In PCI Express case, it's okay. because the block itself is big enough and valuable enough that spreading it out over this many channels is okay. Okay, and I think we will leave routing architecture for next week. So any questions? If not, I actually finished 2 minutes early today, making up for some fraction of being late other days. So, okay, see you everybody.